Yeah, oh, there he is.
He's camera shy.
There.
So we're going to wait a little while, at least until 5 minutes past 1, for latecomers to arrive, since some people may have gone over to 269 Lawrence and get diverted to here. So let's see, the control. Oops, did I do that?
No, I did that, I believe. Doug, you did that.
I did that, sorry, I've got it. Okay, now. Okay, could I ask the people that are sitting over on the right-hand side of the room to move in toward the center? The person in the second row in the white shirt, what's your name?
Me?
Yeah, you. What is your name?
Brian?
Brian. Brian, could you move in somewhere closer to the center? I can't see quite over there very well. And the person behind you as well. So I want to be able to see everybody in the class. You don't need to go to the back. Stay down to the front so I can see your faces. You can see mine. This ought to be reciprocal.
Kip, I've lost control of the camera.
Oh dear. That's maybe because I hit it and tried it. Maybe we need to shut down and dial back into you.
Or maybe it's because you're currently controlling.
Well, I'm controlling far end camera now.
Does that still work?
See, I made the mistake of hitting the control on my camera guy.
Do you want to shut down and you want to call back?
Yeah, let's shut down and call back in.
All right.
If we call you, Guy.
We'll call you.
Because that's what we did last time when it worked.
All right.
Okay.
Okay.
Okay, can you control it now, Guy?
Find out.
Yes.
Yeah, good, good. Okay, and is it set on remote? Far end.
That's it. Now it's good.
Okay, so now let me see what I can see. Okay, so the person in the third row back on the left-hand side in the white jacket over a dark, what's your name?
Pavlin?
Pardon? Oh, that's Pavlin. I can't see your face well enough to recognize you. Could you move in closer to the center? I'm losing you off the edge.
You've already zoomed the camera as well.
Yeah, I want to be zoomed out as far as I am, which I think it is. Okay. Okay. Okay, now one more person, the person in row 3 on the extreme right-hand side. Could you move in closer to the center? What's your name?
Molly?
Molly? Thank you, Molly. Okay, so I think I can see everybody now. interesting.
So that's because, well, no, we've got blocking because it's the lower bandwidth and you're moving the whole picture.
Yeah, okay. Okay, fine. So, okay, are Yanbai and Mihai there, both of you?
Yes.
Yes. Okay, you think we have everybody in that went to the other classroom?
I'd say so.
Yeah. Okay, so then maybe we should begin. So I'd like to welcome you all to the first class in Physics 237 on gravitational waves. My name is Kip Thorne, and I very much want to be called Kip by my first name rather than being called Dr. Professor Thorne or whatever you might be inclined to do. I'm in Cambridge, England this week at a birthday conference for Stephen Hawking and giving a couple of lectures here and having a great time partying with all my friends. But I really wanted to teach this class, particularly since the only two people who could probably have taken it decently are out of town. Sterl Finney's at the meeting of the American Astronomical Society this week, and Lee Lindblom has gone to Japan for the week. So we decided we would try doing this by means of video feed from Cambridge. And I want to thank the people who are responsible for really making this work. Here in Cambridge, Dr. Stuart Rankin, who is the computer whiz in charge of the relativity and gravitation group here, whom I'm looking at the moment, and Neil Scherer, who is Stephen Hawking's personal assistant and often comes to Caltech with Stephen, will be coming with Stephen for 6 weeks in March this year. And over back there at Caltech, Guy Colville and his staff who were there from audiovisual department, and I really appreciate your help. The staff, Lynn and Sergi, I presume you're both there?
Yes.
Now? Yeah, so thank you very much, all of you. Now, let me just verify, can you all see me and hear me all right? Yeah. Okay, thank you. So I would like to, since as long as we have this video capability, I would like to interact a little bit. So I want you to ask questions and have a little bit of feedback back and forth. But let me begin by asking, just for my information, who in the class has never taken a course in general relativity? Would you raise your hands? So that's, I would guess, about half of the class. Who has taken a course in general relativity? Yeah, so it was about half the class. I'm not going to assume that you've had a course in general relativity. I will teach you very quickly that portion of general relativity that we're going to need in the first, in the second week, next week in the class. Let me ask who there is actually registered for this course. Would you raise your hands if you're registered? And who is not registered for the course? Okay, it looks like there may be more people who are not registered than there are registered. But that will make life a little easier on the teaching assistants. So I'd like to go through a few preliminary issues. I will be organizing this course. I will be teaching most of the early lectures, but there will be other people like Sterl Finney, Lee Lindblom, and people from the LIGO project, such as Stan Whitcomb, perhaps some people from JPL working on LISA, who will give some of the later lectures in areas of their own specialties. The TAs for the course are Yanbai Chen and Mihai Bondarescu. Would you stand up and so that people can see who is, that's Yanbai in the back has just stood up. And Mihai is over there controlling the PowerPoint presentation. I can't see you, Mihai, but I presume that's all right.
Yeah.
Okay. Now, I am going to pass out a sheet on course logistics, that is reading, homework, and so forth, on Wednesday. I haven't had time to prepare that yet because I gave one of my lectures here at the conference this afternoon, and so that's slipped through the cracks, but I'll pass that out on Wednesday. You should have 3 handouts that were prepared for you today. You should have a copy of the PowerPoint presentation that I'm going to lecture from today. Do you have that?
Yeah.
You should have a copy of a document about 3 pages long on a list of topics to be covered in the course. You have that one?
Yes.
Yeah. And I'm not going to go through that list. That's just for your information. You can browse it as you will. I'm not going to cover those topics in the order that are written on that list. I just give you the list so you can see in some detail what will be covered. But the third document you have should be a course schedule, which indicates more or less what will be covered when, but in much less detail than in the list of topics for the course. So you have your course schedule there? So let me just walk you through that one. During the first week, that's today and Wednesday, I'll be lecturing from Cambridge here and be giving you an overview of gravitational waves. And we'll do this at basically the level of a physics colloquium. I'll be talking about what gravitational waves are, about frequency bands, the sources in each band, detection methods in each band, wave strengths, various types of gravity wave detectors, gravity wave data analysis, and sources, their phenomenology, astrophysical phenomenology, what science we can learn from them, methods of computing their waveforms, predicted waveforms, and signal strengths. Then in the second, third, and perhaps the fourth weeks, it would probably take me 3 weeks, I'll give you a quick introduction to those portions of general relativity that we will need in the course. I will then apply those general relativity techniques to discuss the physical nature of gravitational waves and their mathematical description in flat space-time, and then propagating through curved space-time using geometric optics. And then we'll talk about the interaction of gravitational waves with an astrophysical environment as they propagate. I'll then spend perhaps 2 weeks, maybe closer to 1 week, on the interaction of gravitational waves with 6 different types of detectors, which I will be introducing in the lecture today. And you'll go through the mathematical analysis of how the gravitational waves influence each of these detectors. And then in the last 3 or 4 weeks of the term, we'll talk about gravitational wave sources. We'll talk about methods of computing the emission of gravitational waves and their waveforms. We'll talk about the astrophysical phenomenology of the various types of waves, and about the dynamics of the sources and the kind of information that the waves carry. So that will get us through this second term of the year, and then in the third term we'll talk in some detail about gravitational wave detectors and detection, going into a lot of detail on detector design, noise sources and their control, data analysis, and plans for these detectors. Now, for those of you who are theorists or are planning to be theorists, let me encourage you with regard to the third term course. I'm a theorist too, but in fact I have found that there is an enormous amount of fascinating physics involved in gravitational wave detectors, and I've learned perhaps more physics as I tried to understand gravitational wave detectors than I've learned in most anything else I've done in my career. And so I will be trying in that third term to bring out the various pieces of physics, teach them to you as we go, as well as the application to the detectors. So do you have any questions about that? Please ask something, just so I know you're alive.
Kip, there's
No questions.
Yeah,
Yes?
There's something that's not relevant to those of us who aren't registered for the course. But
Yes.
Vincent, I've heard some people that that are concerned about the grading for the course. It's currently listed as a letter grade course, and I was wondering if you
Yeah, so this course will be taught pass-fail. It will not be taught with a letter grade. If anybody wants a letter grade, you'll have to petition for the letter grade. And I'm willing to give one if people want it. But I think the only reason anybody would want it is if they're an undergraduate and need a grade on their record for getting into graduate school. Okay, and I'll discuss these kinds of issues on Wednesday, but I'm happy to answer them now if you have specific questions. Okay, no other questions?
How about homework? How's that? Tests and homework, how's that going to work?
Okay, so there will be each week a homework assignment. The homework assignment will be passed out generally on Wednesday, and I will ask you to turn in your solutions the following Wednesday, and the TAs will pass out a set of solutions of their own or their own and mine in exchange for the solutions that you turn in. I will strongly encourage people to work the homework because that's the way you'll really learn the material in the course. And people will be able to pass the course just on the basis of homework, and I hope that that's the way everybody passes the course. For those people who, if there are any who really don't want to do the homework, you can take a final exam in the course instead in order to pass. But I'd encourage you to do the homework instead. And I will very much want feedback from you about the homework. If it's too grungy, too hard, too easy, I want to iterate it as we go along so as to make sure that the homework is really useful for you. Any other questions? Okay, then let's go on to the PowerPoint presentation. Let me bring it up on my screen, and you bring it up there. Okay, is it up?
Yes.
Okay, let's go to slide 2. I'm going to be, for the information of the people in the class, I'm going to be calling for slides on the basis of numbers of the slides that are down in the right-hand corner. Unfortunately, I did not get the technology set up for me to be able to control the PowerPoint presentation from here, nor to be able to control a pointer on your screen to move around to point to what I'm talking about. And so I'm going to try to tell you what things on the screen I'm suggesting you look at as I speak. Please interrupt me at any point that you have a question. I think we'll learn more. You'll learn more by a little bit of give and take than my just talking to you in a monotone. Okay. So let me also say that I can control the camera that's on you, and a guy down there in the right-hand corner of the room can control the camera that's on me. So if you don't like the way I look on the screen, you can ask him to blow me up or whatever. Okay. Okay, so I want to begin by talking about the physical nature of gravitational waves. And so let's look on the right-hand side of the screen. There are two little cubes there that I want to think of as objects. They could be mirrors in a gravitational wave detector that are floating freely in space. Let's imagine they're out in interplanetary space or interstellar space for simplicity, so we don't have to think about how you deal with the Earth's gravitational field that's pulling on them. And suppose that they're completely at rest with respect to each other initially. And let's suppose that a gravitational wave comes along, propagating perpendicular to the screen, and what the gravitational wave will do is it will move these two objects back and forth relative to each other, so that there will be a changing strain in the separation between them. That is a changing fractional separation, delta L over L. And that changing fractional separation is equal to one of the gravitational wave fields that acts on these particles. It's a function of time, and so the gravitational wave field is a function of time at the location of these particles, or these little cubes. It's actually a function of retarded time from the source, because according to general relativity, these gravitational waves propagate at the speed of light. So it's retarded in the same way as an electromagnetic wave is retarded. Now, we can think about these, the gravitational wave in a different manner. Since every object that's at rest initially at the location of the left-hand cube will move back and forth relative to the right-hand cube in identically the same manner, what that must mean is that if we set up a tiny local inertial frame at the location of the left-hand cube and a tiny local inertial frame at the location of the right-hand cube, then as time passes, those local inertial frames that are initially at rest with respect to each other, they will move back and forth relative to each other, which means that they cannot be meshed together to form a single large inertial reference frame. Now that non-meshing, the inability to mesh the local inertial frames together, is quite similar to what's shown in the picture of the Earth on the right-hand side of the screen. Up on the surface of the Earth, you lay down Cartesian coordinate systems over the surface of the Earth, such as those two red Cartesian coordinate systems. There's no way for those Cartesian coordinate systems to mesh together to form a single large Cartesian coordinate system. And of course, we know that the thing that prevents that meshing is the curvature of the Earth, and so it is completely the same with the case of the non-meshing of the local inertial frames in a gravitational wave. The thing that prevents that meshing is curvature of space-time. And so it is that Einstein describes a gravitational wave as a ripple in the curvature of space-time that's propagating through the vicinity of those two green cubes. And those ripples in the curvature of space-time then produce the relative motion of the local inertial frames, or the relative motion of the cubes. So we're going to be developing a description of space-time curvature in a gravitational wave next week, and coming to understand how you can think about gravitational waves in terms of the space-time curvature. These gravitational waves, in fact, then are ripples in the space-time curvature that propagate through the universe. Let's go on to slide number 3. Now, there's a great richness in a gravitational wave space-time curvature. Heuristically, an example is the following, that I've talked about the effect of a gravitational wave in terms of a stretching and squeezing of inertial frames relative to each other. We can also think of that as a stretching and squeezing of space, like you would have if you stretch and squeezed a rubber membrane. On the other hand, if we have a gravitational wave that moves across the left-hand cube, but not across the right-hand cube, so it's rather localized, what you would find is that as the gravitational wave passes, it causes some oscillation in the ticking rate of clocks at the left-hand cube. That is a slowing down of the flow of time of the left-hand cube, a speeding up relative to the right-hand cube. And so a gravitational wave then stretches and squeezes space, but also warps time in an oscillatory manner. And there are other physical effects as well. And the fact that you have these different physical effects is a warning that there's a lot more to a gravitational wave than simply the stretching and squeezing of space. Another example of this is something that I often get asked when I give a lecture to the general public about gravitational waves. Suppose that I have two mirrors, which are shown as cylinders in the diagram, and I have a red laser beam that's bouncing back and forth relative to those mirrors. The laser beam is being used to monitor the motion of the mirrors relative to each other, and this is just what's done in a gravitational wave detector. And I'm often asked, does the wavelength of the light in the gravitational wave get stretched and squeezed in the same manner as these mirrors move back and forth? If that is the case, then obviously you won't be able to see the motion of the mirrors using light. There will be no physical manifestation. But in fact, the answer is no, that space-time curvature influences the light in a different manner than it influences the mirror separations. It's because the light is moving at the highest possible speed relative to the inertial reference frame of these mirrors. And because of that high speed, it feels different pieces of the space-time curvature than the mirrors feel. And so it's influenced in a different manner. And in fact, it turns out that if you adopt the appropriate gauge in general relativity, a concept that we'll introduce next week, then there is, and if the mirrors have a separation that's small compared to a wavelength of the gravitational waves, then the influence on the light is negligible, and it's only the mirrors that move back and forth, and the light's wavelength doesn't get changed at all in that limit. So that's another warning that there's a lot more richness to gravitational waves than just a stretching and squeezing of space. Mathematically, as we will see, gravitational waves are described by a curvature tensor, a so-called Riemann curvature tensor for space-time. This is a fourth-rank tensor, so it has 4 indices on it. And so, again, those 4 indices warn you that there's a great deal of richness in the gravitational wave field. When we go on to slide 4, let me pause here and ask you, are there any questions, any issues you want to raise at this point? No questions? Please ask. Okay. So I'd like to go on with some additional aspects of gravitational waves. The first of these is that gravitational waves are a transverse phenomenon in the same sense as electromagnetic waves are. For an electromagnetic wave, as it goes past an electron, it will, if the wave is propagating into the screen, it will take the electron and move the electron back and forth transversely. That is, the electric field is perpendicular to the propagation direction of the wave. Similarly, for a gravitational wave, if the gravitational wave is propagating into the screen, and if these test masses, shown in green as cubes, lie in the plane of the screen, they will get moved back and forth relative to each other along their transverse direction. But if the gravitational wave is propagating parallel to the screen, well, that is along the direction that links those 2 green test masses, there will be no motion of the test masses at all. There is no stretch and squeeze along the longitudinal direction. There are no physical manifestations of a gravitational wave on the longitudinal direction. Now, another aspect of the gravitational wave is that the stretch and squeeze in the transverse plane are opposite along 2 axes. So if you have a squeeze along the horizontal axis, shown in red on the right-hand side by those tails of arrows, then there will be at the same time a stretch along the vertical axis. The next half cycle, you'll squeeze on the vertical axis and stretch along the horizontal axis. And so the stretch and squeeze are along a set of axes that I have chosen in this case to form a plus sign in the transverse plane. Now, if you look at this force field that is acting, the squeeze along the horizontal axis, the stretch along the vertical axis, at one particular moment of time, you can ask, by what angle do I need to rotate that force pattern to bring it back to the same orientation as it had to begin with? And if you look at the force pattern, obviously, you rotate through 180 degrees. Now, this is by contrast with an electromagnetic wave, where the electric field is the thing felt by an electron that's at rest. And that electric field then points along, say, the direction of that black arrow at the right-hand side of the screen. You have to rotate that electric field through 360-degree angle to bring it back to where it started. So there's this factor of 2 difference in the rotational angle for coming back to where you started, the so-called invariance angle. It turns out that this is an imprint that's left on the classical gravitational wave field and the classical electromagnetic wave field by the underlying quantum mechanical particles that in quantum theory carry the waves. And more specifically, the spin of the particle, the spin of the quantum associated with the waves, is equal to 360 degrees divided by the invariance angle. The invariance angle is 360 degrees for the electromagnetic wave, and so the spin of the photon is 1. It's 180 degrees for the gravitational wave, so the spin of the graviton is 2. This is a specific example of, or a very simple example of what shows up when you do an analysis in what is called canonical field theory, a particular way of describing fields such as the electromagnetic field, the neutrino field, the gravitational field, and other fields that you might imagine occurring in nature. In canonical field theory, if you have a propagating wave, say propagating into the screen, you ask yourself about the following group. You first begin with the Lorentz group. The Lorentz group is the group of Lorentz transformations. Then you look at a subgroup of the Lorentz group. You look at the so-called little group of the propagation vector. The propagation vector is a null vector in space-time. The little group is the subgroup of Lorentz transformations that leave the propagation vector unchanged. You then ask yourself, in the language of group representations, which some of you will have already studied, others of you will study later, what is the irreducible representation of the little group that is generated by the radiation field? And you ask about the order of that irreducible representation, and you find for the photon, the irreducible representation is of order 1, for the graviton of order 2, and those then are the spins of the corresponding particles. So that's the sophisticated description of what's going on in defining the spin and the way that the spin shows up mathematically on the classical field. But the very simple-minded description is the one that I have given you. That reduces to the simple question of what is the invariance angle of a rotation of the instantaneous force field. And from that invariance angle, you can read off the spin. So I would suggest that those of you who have studied the theory of group representations may want to go back and try to think through how do you get from the fancy description of what the spin is down to this simple-minded description. Those of you who haven't studied it, you will pick that theory up, for example, in the mathematical physics course that's taught here at Caltech. Now, just as the electromagnetic wave has two polarizations, the electric field may be polarized in the horizontal direction or in the vertical direction for the two different polarizations. Similarly, the gravitational wave field has two polarizations. And those polarizations show up in the orientation of the squeeze and stretch axes. So if the wave is propagating into the screen and the stretch and squeeze axes form a plus sign, then we call this the plus polarization. The other polarization is something you get by rotating halfway around to where you would get the plus sign again. You rotate just by 45 degrees, you get the cross polarization. Again, this is a consequence of the fact that you have just two polarizations. Even though you have a spin 1 field in the electromagnetic case and a spin 2 field in the gravitational case, and even though you might have expected then that if S is the spin, you might have expected 2S plus 1 different polarization states, which would be 3 for the electromagnetic field. 2S plus 1 would be 5 for the gravitational field. That's not the case. You have precisely two polarization states in both cases. The reason is that in both cases, these waves propagate at the speed of light, which guarantees that the fundamental quantum mechanical particle in both cases has zero rest mass. That guarantees that if you think about the particle spin can only be along the direction of motion or against the direction of motion. It can't point in any other direction, it turns out, when you think about this quantum mechanically. So there are just two helicity states quantum mechanically. That shows up classically in the two different polarization states in the classical field. So again, you see that there is an intimate connection between the underlying quantum theory. And once you've learned how these connections are made between the underlying quantum theories in canonical field theory and the imprints that they leave on the classical fields, there's a lot of power in that. So are there any questions on this subject? It's all crystal clear?
Kip, are there any textbooks that deal with this connection between canonical field theory and gravitation?
I wish I knew one.
What?
No, I don't know where you find that in textbooks. I think I read it when I was a student in an article, probably in Reviews of Modern Physics, around 1960 by Eugene Wigner. And this ought to be in textbooks. Does anybody in the class know where to find this in a textbook? Okay, so this is sort of the lore you pick up when you've been in physics for some 60 years or however long I've been in physics. And there's an awful lot of nice lore like this that should be in the textbooks that is really not. I will see if I can find anything for you, but as I say, that's where I remember learning these things. Other questions? I mean, some of this you get from the theory when you study the theory of group representations, pieces of what I've described, but other pieces you don't. The pieces that you don't get from the theory of group representations, as I say, I think I got those from Eugene Wigner's article in Reviews of Modern Physics, if I am remembering right from my graduate student days in the 60s. So let me go on to slide 5. Still talking. By the way, most of the things that I'm saying here, I'm just telling to you, and most of these things we will work out in the next couple of weeks as we develop the theory of gravitational waves, learn a little general relativity, and develop the theory of gravitational waves. So this is really by way of a preview, an overview of the things that we're going to be studying quantitatively in the coming weeks. So each of the two polarizations has its own gravitational wave field. And so, for example, if I want to talk about the gravitational wave field associated with the plus polarization, I take my two green test masses, the two green cubes that are on the left-hand side of the screen. I orient them in a horizontal manner with respect to each other, and then I just look at how their fractional changes of separation, delta L over L, changes with respect to time. And at that location of those test masses, H plus as a function of time is the gravitational waveform associated with the plus polarization. As I've told you, that gravitational wave field propagates at the speed of light. So if you want to know what the gravitational wave field is at some other location, I have it propagating out of the screen. You just retard the gravitational wave field by in the usual manner for a wave that propagates at the speed of light. If I want to know the gravitational wave field for the cross polarization, I just take my two cubes as shown on the right-hand side, oriented up at a 45-degree angle, and I then monitor their fractional change in separation with respect to time. And these two gravitational wave fields, H plus is a function of retarded time, H cross is a function of retarded time, they will show up next week when we study this subject as the double time integral, two time integrals of certain components of the Riemann curvature tensor. And so we will begin first by introducing the Riemann curvature tensor to describe the waves. Then we will compute how the separation between two test objects changes with respect to time in terms of the Riemann curvature tensor. We will then do two time integrals on it. We will thereby get something that is dimensionless and that is equal to the fractional change in separation of our test masses, and that will be the gravitational wave field. That's not the way it's done in the textbooks, but it will be the way it's done in the textbook that I'll pass out. I'll pass out chapters from an unpublished text on gravitational wave theory that I wrote in the 1980s, but never finished, and so it's just something lying around on my desk. I need some use for it, so I'll give it to you to read. If down in the lower left-hand side, I show examples of waveforms for the two polarizations. These waveforms are just plots of H plus as a function of time and H cross as a function of time. These specific waveforms are an example of the gravitational waves produced by a binary system that is made of a neutron star orbiting in orbit with a black hole, where the black hole is spinning, and the coupling of the neutron star's orbital motion to the spin of the black hole is causing the orbit to precess, and that precession is causing the modulation that you see in those two waveforms, different modulation amplitudes in the two different waveforms. And so in this course, we will work through the details of spin-orbit coupling and binary systems like that, how that influences the waveforms, and we'll derive waveforms such as this. Now, the waveforms are the key thing in gravitational wave observation that we want to go after. These waveforms carry detailed information about the sources, and so it is the waveforms that the observers want to measure. As we will see later on, we can never expect to directly make images with gravitational waves. The reason is that the sources of gravitational waves, as we will study, are sources that in which the waves are produced by coherent bulk motions of large amounts of matter or energy, as in, for example, when two black holes collide. And that means, since the various pieces of the source can't move with respect to each other any faster than the speed of light, and since the emission is being produced coherently by the various pieces of the source, that means that the wavelength of the waves cannot be any smaller than the size of the source. With wavelengths no smaller than the size of the source, you cannot get resolution to do imaging. The reason we can do imaging with me looking at you and you looking at me is that we're looking at waves that have wavelengths that are very small compared to you or me, and that are being with waves that are being produced by incoherent superposition of the motions of electrons in the sources, the electrons in your face as the light bounces off of your face. But in the gravitational case, we cannot then do imaging. What we have to do is look at the time evolution of waveforms. We have to compare them with source simulations, often supercomputer simulations of the dynamics of sources, and try to produce then in source simulations waveforms that match what's seen observationally, thereby trying to unfold what's going on in the source. And so we'll talk about that in some detail a little bit tomorrow, and then in much detail later on in the course. Can we go to slide 6? See how our time's doing. Okay. So I'd like to talk a little bit about the propagation of gravitational waves. Gravitational waves, if they're really true waves, then they have to have a wavelength that is small compared to the radius of curvature of the background space-time through which they're propagating. And so the diagram on the right-hand side is meant to be, this circle is meant to be a picture of what our universe would look like if it's a closed universe. And so the universe is like the surface of a sphere. We've lost one dimension from the diagram. So it's like the surface of a sphere with a gravitational wave in the form of a ripple in the geometry of the surface of the sphere propagating around the sphere. And the wavelength is small compared to the radius of curvature then of the sphere, or the radius of curvature of the universe. This is the so-called geometric optics limit. And gravitational waves make sense as waves only in the geometric optics limit. And under those circumstances, then the waves will propagate at the speed of light, which means the graviton has zero rest mass. The waves then in this geometric optics limit, the gravitational waves, they will be gravitationally redshifted when they climb out of the vicinity of a black hole or a neutron star. They will have cosmological redshifts when they're coming from the early universe. They can be gravitationally lensed, just like light can be gravitationally lensed. We'll work all of this out. We'll develop the geometric optics limit for gravitational waves sometime in the next several weeks. If you're in a situation where the wavelength is comparable to the radius of curvature of the background space-time, then the waves won't propagate as waves. They can be scattered by the space-time curvature. They can be amplified by the space-time curvature. They can be trapped by the space-time curvature and not allowed to go anywhere. And so the behavior can be really quite different from an ordinary wave-like behavior. And we will see examples of that in waves produced in the Big Bang in the very early universe, that get strongly amplified by interaction with background curvature in the inflationary phase of the universe. Gravitational waves then can interact with background space-time curvature when their wavelengths are long enough. On the other hand, as we will see and we'll do specific examples, gravitational waves are never significantly affected by the matter they encounter in the universe. There's negligible absorption, there's negligible dispersion. Dispersion just means that the propagation speed is slowed down by interaction with matter. Dispersion is negligible, scattering is negligible. As a specific example that I will probably give to you as an exercise, let's ask about the biggest dispersion that we can produce. How much can we slow down a gravitational wave as it propagates through matter? Now, let me remind you what produces dispersion. Dispersion in the electromagnetic case is light, say, propagates through glass and is slowed down. What happens is that the electric field in the light wiggles the electrons that are trapped in atoms back and forth, the electrons in the outer shells of the atoms back and forth, and those atoms then scatter the electromagnetic waves when they get wiggled by the electromagnetic waves. This scattering means that, and the scattering is a scattering in the forward direction, but it's a scattering with a little bit of time delay. And so the result then is that this interaction with all the electrons produces a little bit of time delay through the forward scattering, which causes dispersion. So if we want to make the largest possible dispersion for a gravitational wave, we want to have a universe that's filled with the very best gravitational wave scatterers that we can think of. So a real good choice is neutron stars. Neutron stars, a star with the mass of the sun, essentially solid nuclear matter. Neutron stars will oscillate in response to a gravitational wave and re-radiate just like an electron, and do about the best you can do of that, of any kind of form of something that's made of matter. And so what I would like to do is imagine a universe that has nothing in the universe except neutron stars. Then I have a gravitational wave that propagates through this universe that's filled with neutron stars, and I want to ask, by how much can I slow down the gravitational waves? Now, I set down a neutron star density at some level, and then I asked myself a second question at the same time. I asked myself, how big is the universe if it's closed up on itself by the mass of all these neutron stars? And so I have some particular size. It just depends on how close together I happen to have put the neutron stars to form some average mass density. Then the statement that I will probably give you as an exercise to work out is that if I have a gravitational wave field that propagates through this universe filled with neutron stars, that gravitational wave field will suffer dispersion, but in propagating around the universe and coming back to where it started, the amount of dispersion will be a slowing by about 1 wavelength of the gravitational waves, which is a tiny amount of slowing down. And so that illustrates that in the most extreme of circumstances that you just don't get very much dispersion. Similarly, you don't get much scattering or absorption. Negligible in any astrophysical context. Can we go to slide 7? So I now want to turn to some discussion of the gravitational wave spectrum of the waves that are bathing the Earth, and of detectors that operate in the various frequency bands. So the gravitational wave spectrum, the spectrum over which waves that bathe the Earth extend, it extends, that gravitational wave spectrum in which we might expect strong waves extends from about 100 megahertz, 10 to the 8 hertz, on down to about 10 to the minus 17 hertz. At 10 to the minus 17 hertz, the wavelength is about the size of the universe. This is a total of about 22 orders of magnitude, and we will understand when we study waves from the very early universe why no bigger than about 100 megahertz. But I'll leave that, I may say a little bit about that tomorrow. So 22 decades of frequency. It's interesting to recall about electromagnetic waves in an astrophysical context. The electromagnetic waves begin at about 100 megahertz because at lower frequencies than that, the waves get absorbed by interplanetary and interstellar plasma. They begin about where the gravitational waves cut off, and they extend upward by 22 orders of magnitude. So about the same range, 22 orders of magnitude in both cases, but with essentially no overlap, which is an illustration of the fact that really gravitational waves are going to carry a very different kind of information about the universe than electromagnetic waves. Now, there are, in fact, 4 frequency bands in which detectors are operating or will be operating soon with interesting sensitivity. There's the high frequency band, which is frequencies between about 10 hertz and about 10,000 hertz. And this is the frequency band in which operate LIGO, the Laser Interferometer Gravitational Wave Observatory being developed here at Caltech, and so-called bar detectors, large metal bars that vibrate in response to a passing gravitational wave. There is the low frequency band extending from frequencies of about 1/10 of a hertz down to 10 to the minus 4 hertz. And this is the band in which one is searching for gravitational waves using Doppler tracking of spacecraft, an effort that's been underway for several decades at JPL, and in which the Laser Interferometer Space Antenna, LISA, will operate and fly about 2011. There's the very low frequency band with let me switch over to talking about periods, with a gravitational wave period that is about something like a human lifetime, from something like 1 year out to 30 years or 40 years. That is from 1 year out to the length of study of the longest graduate students to get their PhD theses, say 30 years. Well, actually, I knew one that took 11 years. I presume none of you are going to take that long. But the pulsar timing then is a technique that operates in that frequency band. And this is a technique, in fact, that relies on this phenomenon of the warping of time by the passing gravitational wave. If the gravitational wave passes over the Earth, it slows down and speeds up the ticking rates of atomic clocks here on Earth. But it's not passing over the pulsar, and so the ticking rates of the pulsar are unaffected. That means as we time the pulses of a pulsar, we will see the pulsar appearing to speed up and slow down. If we see that with a pulsar that is off in one direction on the sky, and the same coherent changes in oscillatory changes in ticking rates for pulsar in another location on the sky and still another one, we can be fairly sure something funny is going on with our clocks, perhaps a gravitational wave. So that's the third of the techniques and frequency bands. The fourth is the extremely low frequency band of gravitational waves whose wavelengths are comparable to the size of the universe. And it is in this frequency band that we can search for gravitational waves by their influence on the polarization of the cosmic microwave background. The influence on the anisotropy of the polarization of the cosmic microwave background, a technique that was pointed out as a very good diagnostic for these ELF gravitational waves, was pointed out by Mark Kamienkowski a few years ago, and that is now beginning to be pursued. Let's go to slide 8, but let me pause and ask, are there any questions at this point? No questions at all? Okay, let's go to slide 8. This is a quick overview of some gravitational wave sources in our 4 frequency bands. At the top you see in purple the range of frequencies over which gravitational waves from the Big Bang singularity in which the universe was born should lie. These are waves that are produced probably as vacuum fluctuations coming off of the Planck era in which the universe was being created. and then they get strongly amplified by the early inflationary stage of the universe when the wavelengths of the waves are comparable to the size of the radius of curvature of the universe. And these waves should appear over all of these frequency bands. And a goal of this field ultimately is going to be able to map out the spectrum ranging from the ELF band through the high frequency band and thereby get information about the Big Bang singularity. Second set of sources that are shown there with a background that is light green are sources associated with exotic physics in the very early universe. These are phase transitions that occur as the universe expands and cools as the fundamental forces separate from each other. For example, when the temperature has dropped to about 100 GeV, at which point the electric force and the weak force are separating from each other. They were unified earlier in the universe before an era of about 10 to the minus 15 seconds. At about 10 to the minus 15 seconds and 100 GeV temperature, the electric force and the weak force begin to develop their own identities, and there is a phase transition in the structure of the vacuums of these quantum fields. And that phase transition can lead to violence in the early universe if it's a strongly first-order phase transition, which violence can produce strong enough gravitational waves to be seen by our gravitational wave detector. So that's an example. Cosmic stream, domain walls, mesoscopic excitations in the very early universe. There are a number of hypothesized, fantasized, speculative phenomena in the very early universe that could produce very interesting background gravitational waves, and we'll be studying these in this course. Going on down to the blue sources that are concentrated in the low frequency. You notice the exotic physics in the very early universe does not extend into the ELF band. It's concentrated in the other three bands, according to theory. Then in the low frequency band of LISA and Doppler tracking, we have gravitational waves from massive black holes from 300 to 30 million solar masses, from ordinary binary star systems, and from speculative objects such as soliton stars and naked singularities, if you want to be very speculative. Then in the yellow, shown for the high frequency band, in the high frequency band you see gravitational waves from small black holes, stellar mass black holes, between 2 solar masses and 1,000 solar masses, from neutron stars, supernovae, and again speculative objects such as boson stars and naked singularities. So that's a quick overview, and you notice what this means is if you want to study physics in the modern universe with gravitational waves, you want to study phenomena such as stars and black holes, that is going to show up in the low frequency and high frequency bands. It turns out very, very massive black holes will leave some imprint in the VLF band, which I've not shown here, but that's about the only thing in the modern universe that would produce anything below the low frequency band. So the richness of modern universe sources is in the low frequency and high frequency band, and in this course we'll focus almost entirely on those two bands, and we'll focus almost entirely on LISA as a detector and on LIGO and its international partner detectors. We go to slide 9. So this is to give you a feeling for what's going on at Caltech. These are faculty who, together with their research groups, are working on gravitational wave physics or detection. First, with regard to LIGO, Laser Interferometer Gravitational Wave Observatory, operating in the high frequency band, Barry Barish, Ronald Drever, Ken Liebrecht, Alan Weinstein, and I are all working on LIGO in one form or another. Then LISA, the Laser Interferometer Space Antenna, Tom Prince is the mission scientist for LISA, Sterl Finney and I are fairly heavily involved, and there's a very heavy JPL involvement. Doppler tracking of spacecraft, I'm sorry, I have that wrong. The Doppler tracking of spacecraft is being pursued at JPL rather vigorously. And And I skipped over what I've shown here with Kulkarni is not Doppler tracking of spacecraft, that's pulsar timing. And so Sri Kulkarni is involved at a modest level in collaboration with people elsewhere in pulsar timing. And then for the cosmic microwave polarization anisotropy, Mark Kamiankowski on the theoretical end, Andrew Lang and Tony Reedhead on the observational end. So there is a major then Caltech commitment in this field, a far larger commitment at Caltech and JPL than anywhere else in the world. The people who work in this field have, at Caltech and JPL, have formed CAJAGWAR, the Caltech JPL Association for Gravitational Wave Research. We have seminars every other Friday. They alternate with LIGO seminars. There's a website where you can see things that are going on at Caltech and JPL in this field. It has links to LIGO and LISA and other gravitational wave sites. Okay, let's go to slide 10. I want now to begin talking about sources of gravitational waves, and I want to go through a very simple argument that relies on some simple physical arguments and dimensional analysis to get out something surprisingly strong about the nature and strengths of gravitational waves. So let's suppose that I have a source of gravitational waves shown by that green explosion in the upper left, and I have a detector shown by that red V, like it's an icon for LIGO, in the right. And there's a separation between the source and the detector, a separation R. I can take the gravitational wave field H, and as I would do for an electromagnetic wave field, I can expand it in multiple moments of the source's distribution. In the electromagnetic case, you expand in multiple moments of the charge distribution, and you get the electric moments, that is the electric dipole moment, electric quadrupole moment, and so forth. But you also expand in moments of the electrical current distribution, and you get then the so-called magnetic moments, the magnetic dipole, quadrupole, and higher order moments. In the gravitational case, similarly, we can expand in the mass distribution, and we get mass moments. M0 is the mass monopole, which is just the mass of the source. M1 is the mass dipole moment. M2 is the mass quadrupole moment. We can expand in the mass current distribution. The mass current is really basically just the momentum density. So we can expand in moments of the momentum density. And you get then the analog of magnetic moments. You get the mass current moment, S1, mass current dipole moment, S1, which turns out just to be the angular momentum. And S2, the current quadrupole moment, and so forth. And so as in the electromagnetic case, one should be able to expand the gravitational wave field in terms of these moments as a power series or as a series in the moments. And so I'm writing down the terms one after another. And in between terms, I have written an ampersand, and the ampersand means plus terms that have the form of. It means that it's like a plus sign, but with numerical coefficients that I'm not attempting to compute. Now, the first term has got to be dimensionless, and it's got to be, and that first term and all the terms have to fall off as 1 over R. The fact that they fall off as 1 over R just follows from energy conservation, as in the electromagnetic case. The energy density, the energy flux, scales as the square of the field. And so if the field falls off as 1 over R, the energy flux falls off as 1 over R squared. So the total energy flowing through a spherical surface whose area is proportional to R squared, that total energy flowing through a spherical surface will be independent of radius. So the field has to fall off as 1 over R, as in the electromagnetic case. Now the first term then should be the mass monopole moment divided by R, and then multiplied by a g over c squared, where g is Newton's gravitation constant and c is the speed of light, in order to make it dimensionless. And so we can then ask, does this really show up in the radiation field? And the answer is no, and the reason it doesn't is that the mass monopole moment cannot oscillate. Because the mass monopole moment is just the mass, and there's a law of conservation of mass, or relativistically, conservation of mass energy. So although the mass of a source, or its mass energy, can decrease secularly due to gravitational wave emission, that's something at second order in h. That is, h squared, the gravitational wave energy flux goes as h squared, and that can lead to a secular gradual decrease in the mass monopole moment. But it can't oscillate, it can't show up at linear order in h. And so that first term at linear order in h is conserved, it's not radiative, we've got to ignore it. The second term will be a mass dipole moment divided by r, and to make it dimensionless, we have to take one time derivative on it, and then multiply by g over c cubed. That's the only way to get something dimensionless out of the mass dipole moment, the distance to the source, g and c. Only one way is to differentiate the mass dipole moment in time and construct this combination. However, if you think about it, the first time derivative of the mass dipole moment, in fact, is the momentum of the source. And there's a conservation law for momentum that says that the momentum can't oscillate. It can change secularly due to the gravitational waves carrying off momentum, but that's something that shows up at second order in the gravitational wave field, is the square of the gravitational wave field, not at first order. So the first time derivative of the mass dipole moment, the momentum of the source, can't oscillate. We have to ignore that one in the gravitational wave field. We go on up to the next order in this multipolar series, and we will have, in order to get something dimensionless, the second time derivative of the mass quadrupole moment divided by the distance to the source and a g over c to the fourth. And here, for the first time, we find a term that can oscillate in time. And so that means, as we look at things in a multiple moment series, as you would in electromagnetic theory, that it is the mass quadrupole moment that will dominate, and you can't have any lower order waves. Of course, that leaves out the analog of the magnetic moments. And so if you make the same argument with the magnetic moments, the first term is the first time derivative of the current dipole moment. The current dipole moment, as I told you, is the angular momentum. And again, there's a conservation law associated with angular momentum, and so it can't oscillate. That doesn't appear. And the first oscillatory term then is something involving the current quadrupole moment, the expression I have there with two time derivatives. As in the electromagnetic case, you may recall that the magnetic dipole moment, at least for a slow motion source, if it's not oscillating too fast, the magnetic, or if the wavelength is large compared to the size of the source, the magnetic dipole moment is much smaller than the electric dipole moment. And similarly, for a slow motion source with sufficiently long wavelengths, the current quadrupole moment will be much smaller than the mass quadrupole moment in terms of the radiation field. And so the radiation is still dominated by the mass quadrupole moment. The current quadrupole moment turns out to be down by one factor of v over c, where v is the internal velocity of the source from the mass quadrupole moment term. And so the mass quadrupole moment term is the dominant term, and we have deduced then that at least in the case of slowly changing sources, where the wavelength of the waves is big compared to the size of the source, the gravitational wave field will look like g over c to the fourth times the second time derivative of the mass quadrupole moment divided by the distance to the source, of course retarded, that the mass quadrupole moment evaluated at the retarded time. So we have derived this without using any general relativity, just simple physical arguments, and it has to be true then, similarly in other theories of gravity, it should also be true. Now, if you go to canonical field theory, you have another way of learning the fact that it's the mass quadrupole moment that should be the first radiative moment, at least in the case of general relativity. That is that in canonical field theory, there's a fundamental theorem that says that if you have a source that is radiating some form of radiation field, and that radiation field is carried by quanta that have some spin s. That spin would be 1 for the photon, for electromagnetic waves, 2 for the gravitational waves. And this theorem in canonical field theory says that if you take the radiation field and you expand it in multiple moments defined or in spherical harmonics, in angular spherical harmonics, that the multiple orders that will appear in the spherical harmonics are only orders that are bigger than or equal to the spin of the quantum. That means in the electromagnetic case, you only have, because the photon has spin 1, you only get waves of multiple order dipolar, that is L equal 1 and higher. In the gravitational case with spin 2, you only get waves that have quadrupole order and higher. And similarly, if you had a radiation field that whose underlying quanta had spin 3, you would only get octupole order and higher. So clearly there must be some fundamental relationship between the conservation laws that are showing up here and this issue of the spin of the quantum. But that's something that I have actually never seen really worked out in detail. These are two different ways to get at this basic issue that we will see as the leading order form of radiation, mass quadrupole radiation. Okay, any questions about that? Some of this is a little bit sophisticated, but it's probably sufficiently simple that I should speed up. Is that right? Shall I speed up? Don't sit there like lumps on a log. Tell me what I should do.
I think the variance in the audience is so huge, Kip, that
okay.
we've got postdocs here and undergrad, so
okay. So
pretty hard to figure out.
So I will plod along, but we'll get much more sophisticated next week. So let's talk about the actual strengths of the gravitational waves. Suppose we have a source that has a mass m, a size L, and it oscillates with a period p. Then the mass quadrupole moment will be of order the mass times the size of the source squared, ml squared. If you then go in and look at the quadrupole moment approximation, let me tell you, if you guys don't wiggle in your seats, the screen freezes and I can't see you at all. Will you wiggle just a little bit? Okay, thank you. So you look at the mass, the mass quadrupole moment looks like ml squared. And so that formula we have for the gravitational wave field in terms of the second time derivative of the mass quadrupole moment looks like a g over c to the fourth, a mass L squared divided by the period squared to get a second time derivative and divided by distance to the source. Now, L squared over P squared is basically the internal velocity of the source. The size divided by the period of oscillation is the internal velocity. And so ml squared over P squared is the kinetic energy of the source, the internal kinetic energy. And that means that the gravitational wave field is approximately equal to g over c to the fourth times the internal kinetic energy divided by the distance to the source. Now, if I divide the internal kinetic energy by c squared, I basically convert it from energy units to mass units. That's the mass equivalent of that much kinetic energy. That's how much rest mass we would get out if we were to convert that internal kinetic energy into a mass. And if I multiply that by g, I then get the Newtonian gravitational potential produced by the mass equivalent kinetic energy. I then divide by c squared and I get something that is dimensionless. And so the statement is that the gravitational wave field is approximately equal to the Newtonian gravitational potential in magnitude. It's the Newtonian gravitational potential produced by the kinetic energy, the internal dynamical kinetic energy of the source, converting it into mass units, divided by the speed of light squared to make it dimensionless. Now, for all the sources that we will study in astrophysical sources, realistic astrophysical sources, the internal motions are produced by strong internal gravitational fields. And that means by the virial theorem that the internal kinetic energy is approximately equal to the internal gravitational potential energy. And so the H can also be regarded as 1 over c squared times the Newtonian potential produced by the gravitational potential energy of the source. And when you look at it that way, you see the nonlinearity that comes out in general relativity. It's the gravitational energy oscillating that produces the gravitational wave field. And we will in fact derive a formula that is basically of this sort next week or the following week that really shows this nonlinearity in a clear way. The contributions from the higher order multipoles are down by v over c to some power, where v is the internal velocity in the source, and as I've mentioned before. And so this is the dominant contribution to the gravitational wave field. If we now put in some numbers, gravitational waves, say, from colliding black holes or colliding neutron stars, as we will see when we look at the phenomenology of sources, the characteristic distance to the nearest such source of colliding black holes or neutron stars that we might expect to see every year from Earth, that distance may be something like 100 megaparsecs. Now, one parsec is an astronomer's unit that's approximately equal to 3 light years. That's about 300 million light years to this source, 3 times 10 to the 27 centimeters. For these sources, black holes or neutron stars that are colliding, they're moving close to the speed of light, and so the internal kinetic energy is of order of the mass of the sun. And so if we feed that into our formula for the gravitational wave strength, we will, and feed in the distance to the source, we will wind up with an h of a few times 10 to the minus 22. And so that's what sets the scale that we must use for gravitational wave detectors. We need to get down to h's that are smaller than about 10 to the minus 21 if we're going to have much chance of seeing gravitational waves. Can we go on to slide 12? Are there any questions? Okay, then here I just remind you then that one of the techniques to look for gravitational waves is with bar detectors. This was the technique pioneered by Joseph Weber, in which you have a large metal bar, aluminum or in one case niobium, masses that range from a few tons to a few tens of tons. When a gravitational wave comes by, it drives the end-to-end vibrations of the bar. And so I just show this slide to indicate that there is now in operation a worldwide network of bar detectors like this, where the detector's cryogenically cooled. There's one at Louisiana State University in the United States, in Perth, Australia, at CERN in Geneva, Padova, Italy, and the University of Rome. And these are sitting there at this moment doing data runs. They've been doing data runs for the past several years at good enough sensitivity that they could see gravitational waves, but not good enough that they have a very high probability at all of seeing them. Let me turn to interferometers, and I'm going to talk a bit about interferometric detectors, and then I'll quit for the day and we'll continue on Wednesday. So this is a schematic diagram of a LIGO interferometer. And we'll talk about these interferometers in detail later, but the basic idea is as shown here on the upper right-hand side of the screen. You have 4 test masses in the form of cylinders that are made in the initial interferometers. They're made of fused silica, that is quartz. Each of these cylinders has a mass of 11 kilograms in the first LIGO interferometers. And when the gravitational wave goes by, it moves them back and forth relative to each other along these 2 orthogonal arms. So moving apart along one arm and moving together along the other arm, and the next half cycle moving apart on the second arm and together on the first arm. And so we use a technique of laser interferometry to monitor those motions. And I think I'm not going to go through the details of just how the interferometry works. We will discuss that later. But the bottom line then is that in the interferometry you wind up with an intensity of light going into the photodetector that is directly proportional to the time-changing difference in arm length along the 2 arms. Putting in numbers, we have chosen to operate with an arm length of 4 kilometers in LIGO. The H's that we need to get to are 10 to the minus 21 or smaller, and so the challenge is to monitor time changes of those separations of these cylinders by an amount of about 4 times 10 to the minus 16 centimeters or less. That is 4/100ths the diameter of the nucleus of an atom or less. And so we will be discussing in some detail how one goes about doing that. In slide 14, we have a photograph of one of the sites at which the LIGO interferometers is operating. This is what you see is a corner building in which the corner test masses, the photodetector, and the laser sit. You have end buildings way down in the distance, down along the vacuum pipe that you see the vacuum pipe there in the picture. And the end mirrors are way down at the end of that long vacuum pipe. There actually is one 4-kilometer interferometer operating at Hanford and one 2-kilometer interferometer operating in the same vacuum pipe. Let's go to slide 15. There is an identical facility in Livingston, Louisiana, except that in this facility we have only a single interferometer, a single 4-kilometer interferometer. The reason we have 3 interferometers is 3 is what we believe will give us high confidence that if we see the gravitational wave simultaneously in all 3 interferometers doing the same thing, high confidence that that's really a gravitational wave and not due to some chance noise source that just happens to go on in a noisy way, in a similar noisy way in all 3 interferometers. So for high confidence of detection, we need all 3 interferometers. These 3 interferometers are now up, they're operating, they're locking robustly, and the first data run with a serious analysis of the data to look for gravitational waves began on December 29, about a week ago, a week and a half ago. These interferometers are not yet at design sensitivity. They will be roughly a year from now, I would guess. And then from then into about 2006, we will be carrying out gravitational wave searches with a sensitivity at which it is quite plausible for us to see gravitational waves, but not a high probability. Then in 2007, we will upgrade to advanced interferometers with a 3,000 times higher event rate and perform a new search at a sensitivity where there should be a variety of sources that are easily strong enough for us to see. And so if we're a little lucky, we will see them with the first interferometers. If we're unlucky, we will have to wait for the advanced interferometers. By the time of the advanced interferometers in 2008, we are almost guaranteed to be doing very rich science. The LIGO is organized as shown in slide 16. There is a LIGO laboratory, which is a Caltech MIT facility with Barry Barish as the director. And the LIGO laboratory is responsible for the facilities and for the design, construction, and operation of the interferometers. Then there's a LIGO scientific community, which consists of 350 scientists and engineers at about 25 or 30 different institutions around the world, including Australia, Britain, and France, India, Japan, Russia, as well as the United States. And the spokesman for this LIGO scientific community is Ray Weiss. This community formulates the science goals, carries out interferometer R&D, and I left off the most important thing here. It does the gravitational wave searches, plans them and carries them out, analyzes the data. And so the science is done by the science community. And we are but one of about 25 or 30 institutions involved in the science. LIGO is shown on the slide 17. LIGO is 2 facilities in an international network that includes a detector in Pisa, Italy called the Virgo detector, which is a French-Italian collaboration. The Geo 600 detector in Hanover, Germany, which is a British-German collaboration. And a Tama 300 detector in Tokyo, Japan, which is actually a prototype for a 3-kilometer detector that they plan to build in the middle of this coming decade. This full network is required for detection confidence in order to extract both waveforms in order to determine the direction of the source. LIGO by itself cannot determine the direction of the source. It by itself can get only one waveform. So we have to have our international partners, as we will see when we go through the details, in order to get both waveforms and in order to extract both waveforms and determine the direction of the source. In slide 18, you see pictures of our partner facilities that I was discussing. I think I will stop for today and begin on slide 19 on Wednesday, when I'll go in a little bit into the various noise sources and get a little bit of feeling for what's going on in interferometers and practical interferometers. So I'm going to then talk about the interferometers in a little more detail. I'll talk about LISA, about data analysis, and then we will go through an iteration of a number of sources that we expect to be able to go after and the science that we expect to get from them. Those are the things I'll discuss on Wednesday. And then next Monday, we'll begin an introduction to gravitational wave theory and the theory of gravitational waves themselves. So are there any questions as we wind up here?
We have class here on Wednesday and then in
Well, I'm sorry, class on Wednesday will be in 269 Lauritsen and not here. But we will have the same system set up to do it in 269 Lauritsen. We also have a backup. If somehow the internet goes down, we will switch over to an analog telephone line, and I won't be able to see you. We were lucky today, and I want to again thank the people who really made this happen here in Cambridge and there at Caltech. Other questions?
I'm curious about the dispersion relation of the gravitational wave, the matter.
So a question about dispersion relation for a gravitational wave going through matter.
Yeah, how does
So
it wavelength?
Pardon?
How does it, in your specific example, how does it depend on the wavelength?
Okay, so as in the case of electromagnetic waves going through matter, the dispersion relation can be very complicated depending on the details of the form of the matter. If you go through a plasma, you have a different dispersion relation than if you go through glass, for example. And so similarly for gravitational waves, the dispersion relation will depend on whether the matter is a swarm of neutron stars or a swarm of black holes, or whether it's just a plasma. This dispersion will always be very, very small in magnitude, but the dispersion relation can be equally complicated to what it is in the electromagnetic case, just depending on the nature of the matter. It's never of any practical significance as far as I've ever been able to see, but it is an interesting issue of principle. And I will have you work out the dispersion relation for at least one form of matter, maybe more. And I'll give you a little bit of reading about this subject. Any other questions? Okay, I'll see you on Wednesday. Thank you.